In bsci lab number 2, we're going to take a look at Ospf. Open Shortest Path First is what that acronym stands for. Ospf, it's a link state routing protocol. It uses the Dijkstra algorithm to calculate the shortest path to destinations in the network. And from your studies of Ospf, you might recall that there are multiple Ospf network types. In this lab, we're going to mainly focus on a couple of special considerations for a non-broadcast Ospf network. That's what we have by default on a frame relay serial interface. And we also have multiple areas in this lab. We're going to begin this lab with a bit of review. We're going to review the Ospf network types. Then we'll take a look at configuring Ospf, again with a special focus on non-broadcast network considerations. After configuring Ospf, we want to verify our neighbors, our Ospf adjacencies, as well as router IDs. A router ID is the IP address that a router is known by inside of Ospf. And of course, we could have multiple valid IP addresses on a router. We'll discuss which IP address is used as the Ospf router ID. And in our particular topology, the way the areas are laid out, we're going to see that we have a need for a virtual link. We'll talk about why we might need a virtual link and see how we can configure a virtual link. And finally, after we do configure this virtual link, we should have full reachability throughout the network. And we'll see toward the end of this lab how to verify that end-to-end connectivity. Let's begin, though, by reviewing the Ospf network types. The table you see on screen can serve as a reference for you, but let's touch on some of the high points together. In a broadcast Ospf network, we might have multiple routers connected to an Ethernet segment. They're all part of the same subnet. And instead of having every router on that subnet form an adjacency with every other router on that subnet, Ospf elects a DR, a designated router, and also a BDR, a backup designated router. That way, all of these various routers on the subnet, they don't have to form adjacencies with each other. They only have to form adjacencies with the DR and with the BDR. And a broadcast Ospf network type is the default network type on a LAN interface, such as an Ethernet or fast Ethernet interface. And since it is a broadcast type, the neighbors are going to be automatically discovered. We don't have to statically configure our Ospf neighbors. Similar to a broadcast Ospf network type, we have a non-broadcast type. That's the default Ospf network type on a frame relay serial interface. Here, because this is a non-broadcast environment, we might have to statically configure our neighbor. Again, all routers are on the same subnet, and we do have a DR, and we could also have a BDR. In a point-to-point Ospf network type, we have a router on each end of a point-to-point link. This is the default type for non-frame relay serial interfaces. Each of our point-to-point links exist on a separate subnet, and there is no DR in this environment. And finally, a point-to-multipoint Ospf network type, even though that is not the default network type on any of our interfaces, it can be configured on any type of interface. Our Ospf neighbors are automatically determined, all routers are on the same subnet, and there is no designated router in this environment. Before we go into the router interface, let's take a look at the topology that we're going to be working with. Let's say that router R1 on the screen exists at a corporate headquarters, and we may have multiple remote sites connected to our frame relay service provider. However, in this lab, we're only going to configure one remote site. We go into that remote site by going into router R2, and sitting behind router R2 at that remote site, we have routers R3 and R4. Remember, the default network type for our frame relay serial interface is non-broadcast, and in a non-broadcast environment, we need a DR, a designated router. And I would say that a good choice for a DR in this environment would be router R1. That's the headquarters site. If we were attaching to multiple remote sites, R1 could be the hub in a hub and spoke type of topology. That is something that we want to configure in this lab. We want to influence router R1 to become the DR. And we do not want router R2 to become the DR. Since this is a non-broadcast network, we need to go to router R1 and specify who its neighbors are. In this case, it only has one neighbor, router R2, but we will want to statically configure that. That will not automatically be learned in a non-broadcast environment. Another OSPF design consideration deals with router ID. The router ID is the IP address by which a router is known in the OSPF process. And a router's router ID can automatically be determined. Here's the way it works by default unless we override it with a static configuration. The router ID is going to be the highest IP address on any active interface. However, if we have configured a loopback interface, the loopback interface's IP address, that's going to be the router ID. And the table on screen shows you how we are influencing the router IDs. To make it easy for us to visualize which router we're dealing with, what I like to do is go in and set up a loopback interface on each of the routers. For router R1, the IP address of that loopback interface is 1.1.1.1 with a 32-bit subnet mask. Similar for R2, we have 2.2.2.2, and I've used the same strategy for routers R3 and R4. That way, as we're examining the output of our show commands, we can readily determine the identity of a particular router. Let's review the syntax we're going to be using. To enable OSPF on a router, we're going to say router OSPF and then provide a process ID. This is a locally significant process ID. Unlike EIGRP, where the autonomous system numbers had to match between neighbors, that is not a requirement for OSPF. However, as a best practice, I like to keep the process ID the same. However, it is not required. This command then takes us into router configuration mode. It's from router configuration mode where we can specify the networks that are participating in this OSPF process. We give the command network, followed by the network address, followed by a wildcard mask, much like we would do with an EIGRP network command, but then we specify area and give a number for that area. OSPF allows us to divide our network up into different areas, and this multi-area approach can give us greater scalability by preventing the flooding of complete route information throughout all of our areas. And if we do have more than one area, we must have a backbone area, and that backbone area must be numbered 0. And since part of our topology is using a non-broadcast OSPF network type, we need to go to that DR, the hub and a hub-and-spoke topology if we had multiple remote sites, and specify the IP addresses of our neighbors that we wish to form an adjacency with. So what we will want to do is go to router R1 and give the command neighbor followed by the IP address of router R2. And since we do want router R1 to become our designated router, we want to influence that as well. The way we can do this is by going into the serial 0/0 interface of router R2 and specifying that interface's OSPF priority is 0. By setting the OSPF priority to 0, we are preventing that interface from participating in the DR election. The command we're going to use to accomplish this in interface configuration mode is IP OSPF priority 0. That's our game plan. Let's now go out to the router interface and walk through the configuration together. Let's begin our configuration on router R1. That's the router that we said would be acting as a hub if we had a hub-and-spoke type of topology. In router R1, let's enable OSPF with the command router OSPF, and let's give 1 as the process ID. Now, using a series of network commands, we can specify which networks are participating in this OSPF process. First, we specify network 10.1.1.0, and it has a 24-bit subnet mask, which gives us a wildcard mask of 0.0.0.255. It belongs to area 0. We do the same thing for network 10.1.2.0, and we also have a loopback interface, 1.1.1.1. We want that to participate in area 0 as well. This time we give a wildcard mask of 0.0.0.0. Something else we want to do here, though, Because we're in a non-broadcast environment, we want to use the neighbor command to specify that our OSPF neighbor lives at IP address 10.1.1.2. Before we move on to router R2, let's give a show command. Let's do a show IP OSPF interface serial 0. Let's just verify that the network type on this frame relay interface truly is non-broadcast. We also see that the router ID, that's our loopback address, 1.1.1.1. Now, let's move over to router R2 and configure it for OSPF as well. In global configuration mode, we first go into interface serial 0/0. The reason we want to go into a serial interface is we want to prevent this interface from participating in the DR election. To prevent that from happening, we say IP OSPF priority 0. Now we're ready to enable OSPF on this router. We do that with the command router OSPF 1. That 1, by the way, did not have to match the 1 on router R1, but as a best practice, I like to do it that way. Now we give a series of network commands. Network 10.1.1.0, and we have a 24-bit wildcard mask. That network is in area 0, but this is an ABR, an area border router. An area border router has at least one interface in area 0 and another interface in another area. In this case, we have network 172.16.1.0 sitting in area 1. That makes this router an ABR. We also want to educate OSPF about our loopback interface, 2.2.2.2. We'll say that it belongs to area 0. And like we did on router R1, let's hop out and give a show command. Let's say show IP OSPF interface serial 0/0. Let's again verify that this is a non-broadcast interface. We see the router ID is 2.2.2.2. That's our loopback IP address. Let's also do this. Let's say show IP OSPF neighbor. Let's see if we have formed an adjacency with router R1. And yes, indeed, we have. We see router R1's router ID, and we also see that it's the DR. It's the designated router. That was our goal. That's what we were trying to accomplish. Now, let's move over to router R3. On router R3, our interfaces are on Ethernet segments. In other words, we're going to be using the broadcast OSPF network type instead of non-broadcast. On router R3, we still enable OSPF like we did before by saying router OSPF 1. We give the network statement of network 172.16.1.0 with a wildcard mask of 0.0.0.255. That network belongs in area 1, and since we're dealing with a fast Ethernet interface here, we do not have to be concerned with issuing the neighbor command. We can just specify our networks using the network command, and our neighbors, they'll automatically be discovered because we are on a broadcast segment. Our other network in area 2 is going to be network 192.168.1.0, and since it has a 24-bit subnet mask, that gives us a wildcard mask of 0.0.0.255, and we say it belongs to area 2. And notice the adjacency message that popped up on screen. It's showing us that router R2 is now our neighbor. We specify the loopback address. We're going to say network 3.3.3.3, and because we're using a 32-bit subnet mask for these loopback addresses, that's the reason our wildcard mask is 0.0.0.0. This loopback lives in area 1. Let's do a show command. Let's say show IP OSPF interface. This time, we're looking at fast Ethernet interface 0/0. Notice that the default OSPF network type on this type of interface is broadcast. We're verifying our router ID is 3.3.3.3. Let's do a show IP OSPF neighbor to make sure that we formed an adjacency with router R2. Indeed, we have. Router R2 is the DR on this Ethernet segment between router R2 and R3. If we do a show IP route, we can see that yes, indeed, we have learned routes via OSPF. And notice, we have the IA tag saying that these are OSPF inter-area routes. We're learning routes from other OSPF areas. Interesting, interesting. Well, let's continue in our configuration. We have one more router to go. Let's go over now to router R4. Router R4 has all of its interfaces in area 2. Let's go in and enable OSPF with the command router OSPF1, just like we've been doing. One of R4's networks is 192.168.1.0. Everything in our topology has a 24-bit subnet mask except for those loopback interfaces. So we give a wildcard mask of 0.0.0.255. This lives in area 2, and we also want to specify our loopback interface. 4.4.4.4 with the wildcard mask of 0.0.0.0 living in area 2. Let's make sure that we have formed an adjacency with our neighbor, router R3. We can do a show IP OSPF neighbor to confirm that. We have, it looks like our neighbor is the DR on this Ethernet segment. Let's see if we've learned routes via OSPF. And we have not. We definitely have an issue. The only networks we know about are connected networks. We have learned nothing via OSPF. Let's go back and take a look at our topology and see if we can figure out what's going on here. As we examine our topology on screen, I think we may see a violation of a critical OSPF rule. OSPF has a requirement that says all non-backbone areas must touch the backbone, and our backbone area is numbered area 0. And we don't have an issue with area 1. R2 touches both area 0 and area 1. However, area 2 is not adjacent. Area 2 is not touching area 0. That is a problem. That is the reason that we are having an issue learning OSPF routes on router R4. How can we fix this? A fix for this type of situation, other than going back and redesigning the network, is to use a virtual link. A virtual link logically ties together the discontiguous area to the backbone. In this case, we will want to go to router R2 and R3 and create a virtual link. What we will do, we will give a command on R2 to point to the router ID of R3 and say we want to create a virtual link with that router ID. And we'll do the same thing from the perspective of router R3. Let's check out that syntax. What we're going to be doing, we're going to say in router configuration mode, area, we give the number of the area that we're crossing, the transit area if you will, followed by virtual -link, followed by a router ID. That's the router ID of the other router on the other side of this link. We're going to be issuing this command on both routers, the router on each side of that link. Again, the number, that's the number of the area that we're crossing, and the router ID, that's the router ID of the router on the other side of the link. Let's go back out to the router interface and set this up. Let's begin our configuration on router R2. We go into global configuration mode, then go into router configuration mode for our OSPF process, and we give the command area1 virtual-link 3.3.3.3. What we're doing here is we're saying we want to create a virtual connection, a virtual link across area 1. At the other side of this link is a router that has a router ID of 3.3.3.3. Router R2, it is touching area 0. We want to link over to router R3, which is not touching area 0. Let's now go over to router R3 and give sort of a mirror configuration. On router R3, let us once again go into router configuration mode by saying router OSPF1, and we give a similar command. We say area1 virtual-link followed by 2.2.2.2. This is the router ID of router R2, the router sitting at the other end of that link. Once this virtual link has been set up between areas 2 and 0, the backbone area, we should now be advertising routes from Area 0 into Area 2. Let's make sure the link is up and functioning. We can say show IP OSPF virtual-link. Let's take a look at the status on the screen. It looks like the link is up. We have a link formed with a router ID of 2.2.2.2. That's excellent news. At this point, let's go over to router R4. Remember the issue we're trying to overcome. Router R4 had not learned any routes via OSPF. Now that we have this virtual link established, let's see if that has changed. On router R4, we do a show IP route. Look at this. Great news. We have learned inter-area routes via OSPF. And as a best practice, we should copy our running configuration to the startup configuration. This is something you want to do on the exam. At the end of your configuration on the exam, be sure on every router to say copy running-config, startup-config. Let's review where we have been in this lab. In this lab, we configured an OSPF network. Specifically, we configured a multi-area OSPF network that used the non-broadcast OSPF network type, in addition to the broadcast type. Since OSPF does have different network types, we began our discussion with a review of the various OSPF network types. Then we talked about the syntax required to configure OSPF on our routers. After a basic OSPF configuration, we saw that we could use show commands to verify our OSPF neighbors and to check out the router IDs, the IP addresses that the routers are known by inside of the OSPF process. But then we had an issue. We had an issue with router R4. It had all of its interfaces in Area 2, and it had not learned about any routes via OSPF. And after examining our topology, we discovered that Area 2 was not adjacent. It was not connected to the backbone area, Area 0. To fix that, we said that we could use a virtual link. We could virtually span Area 1 in our case to make Area 2 appear to be adjacent to Area 0. And we saw the syntax to configure that. Once we had configured that virtual link, we looked at the routing table on router R4 and we verified that we now had full reachability throughout the network. And we concluded with an exam tip, and that is we should always copy our running configuration to the startup configuration on our routers before concluding the exam question.